right, here we go, guys. Here we go. All right, yesterday, we talked about how we are given a table of values. We can determine, at this point anyway, if it's linear or quadratic. And what was the key? What did we do? We found our rates of change. And if they were all the same, all the way down the table, the rate of change, slope, keeps coming out the same, then we know it's linear. What happens if it's quadratic? Yeah, then the rate of change is linear. So if you are determining your rates of change and you're getting numbers like this, that's quadratic. Because the rates of change, these are the rates of change. The rates of change are changing linearly. They're changing by the same amount. Either goes up or down, changing by the same amount. Okay? Now today, we're going to figure out concavity from the rates of change. Alright, so the average, there's a typo there, should be the average rate of change over equal length input value intervals is increasing if the thing is concave up. So the average rate of change is increasing. If it's concave down, the average rate of change over equal length input intervals is decreasing. And notice he puts in a caveat over small intervals. So you can't look at the first number in the t-chart and the last number in the t-chart. You have to look at little intervals to make that determination. So would you find, for example 4, would you find the average rates of change for each table? So, do you understand what I'm asking you to do? Just what we did yesterday. So for the first table, we have 1, 4, 1, 1, 1. So I want you to find the average rate of change. So here we have -3. Here we have 0.1. So the average rate of change would be -3 over 0.1, or what is that, -30? And now we'll do the same thing for the next. Do the same thing here. The average rate of change for the next pair and the next pair. And I want you to do that for all 3 tables. And then we're going to talk about what kind of concavity we have. I don't either. Alright, we'll get busy, Cole. I'll tell you what we're doing. Sylvia, you got all these done? Yes. Alright. I want you to come up then and put your average rates of change on the board. So I did A. here are my average rates of change over here. You don't have to do everything, but put B and C, your average rates of change up here.
Wait, so how much?
No. Oh. Wow. I thought Sylvia was over there messing around, but she wasn't. She was working hard. And I agree with her completely. I did these, this was A. Look what's happening to my average rates of change. What's happening to them? They are increasing, and that means I am on a up. When she found the average rates of change for the second table, the average rates of change were all the same, which means we're not going to discuss concavity, because if they're all the same, it's linear. And then here, they were decreasing, so that meant it's concave. We good with that? Beautiful, beautiful, beautiful. Okay. Go to the back of the next page where it says check your understanding. Get with your partner and let's spend a couple minutes seeing if you can figure out the check your understanding on the back of the U-Haul page. On the back of the U-Haul page. Oh, yeah, the whole thing. We do the whole paper.
Yeah, but I'm saying for linear ones, you don't have to do that. You can just do
And then we're gonna talk about it. All right, girls, got all of them?
I won't change this. That's 40. I said it's too late.
All right, are we ready to chat? Here we go. Number one, at what rate is the air mattress being deflated? Charlie?
Negative 75 over 2.
So negative 37.5 units.
Oh, I see.
Yeah, I mean, yeah, it's fine. It's 75 over 2 is fine, usually for that kind of problem with a decimal, but it's fine. 75 over 2 is fine. Negative, right? Units, cubic feet per, what is it, minute? Cubic feet per minute. Remember, with our rates of change, we should always have a unit if it's an applied problem. Is this a T-chart? No. All right, number B, letter B. Find the volume of air remaining in the mattress after 5 minutes. What did you do there? Describe.
112.5.
112.5 cubic feet. And how did you do that?
I made the equation based on the slope and then the
So what equation?
negative 37.5 x plus 300. And then
So
plus
she actually physically made an equation. Is that okay with everyone? And then plugged in
5 for x.
5 and did the math. Okay? All right. How about C? Does the air mattress lose at a faster rate during the first 5 minutes or during the last 5 minutes? It's linear. So what is the rate of change doing? Nothing. It's staying the same, right? Beautiful, Celeste. Beautiful. Thank you. Okay. Number 2. The function is linear with f of 4 minus f of 1 equals negative 27. What is the rate of change of f? He got negative 9. He got right. Explain how you did that, Will.
So, the average rate of change is f of x minus x. And so then I just put 27 over 4 minus 1.
Exactly. Remember that thing I want you always to write down, or I don't want you to write down. The AP people want you to write that down every time. And if you think about that, doesn't that make sense? He knows his top is 27 and negative 27. They tell him. Obviously, the bottom is 3. So there you go. So, what would f of 11 minus f of 8 be? It's linear. What's the difference between 11 and 8? 3. So won't it be negative 27? It's linear, guys. So the difference from 4 to 1 is gonna be the same as the distance from 11 to 8? And then what about C? The rate of change doesn't change in a linear function, right? So if you have f of 20 minus f of 15 over 20 minus 15, isn't that the average rate of change? And what do we know about the average rate of change in this problem? It is -9. -9. Are we good? All right. How fast does a penny drop? Take a minute with your partner and see if you can figure out anything in 1 through 8. Do as much as you can, or all of it, in 1 through 8. How fast does a penny fall from the Empire State Building?
the same thing that,
We all multiples of 64.
An increase of 520.
So,
yeah, I did that, but I
Like the rate of change increase
No.
of 520.
Well, so what do you think? When you're looking on it,
right, but
No, but not.
it increased by the fall, means the rates increased by 128.
increases 128 feet each second.
I think so.
Each 2 seconds.
Each 2-second interval.
Why would they change? So that's
The
64 divided by 2. I know, no, big lot. 32 right?
192 over 2.
It's like
128.
This is yeah, because then it would be 320 yeah. No, once again,
oh,
Like each.
not 60 minus.
So each 2 minus each 1 or 0. 2.
St. X.
They're all quite good.
Yeah, they're pretty good this year.
Yeah, but
All right, how are we coming, guys? Anybody have a table you can put on the board for number 1? Even if you're not done with all of them, you got a table, you can get the conversation started. Like, Caitlin, put your table up there. Anybody figure out number 2? You can put your work up here for number 2. Look out. I want to call on someone, the volunteers. Thank you, Carter, for your unit 2. Anybody comfortable with the number 3? Okay. So let's start with this conversation. We'll go from there.
Yep.
Training?
There's some training. We do most of your training since everyone's
All right, let's check her table 1, or number 1, her table. Those look like the same numbers I got. Are you okay with that? Parker, how did you do number 2?
I just set like the height is 0.
Yeah, so they gave us the equation there that gave the height. They said if I'm on the ground, my height 0. What, you subtracted, divided, and square rooted? Okay, that'll work. Now notice, he did not like actually on his calculator type that in because of the word exact in number 2. See that word exact? That means no rounding off. Now Sam actually used that number in his problem, but Parker didn't do that number because that word exact is important. All right, and then negative 141. This is one of those times, Sam and everybody else, where we really have to be careful. Okay, so this is the exact value. Okay? This is the rounded off value. When I did it with the exact value on my calculator, I got negative 141.421. See how it's off a little bit? So, again, in general, don't round until the final ending. If you do intermediate rounding, it can throw things off. And I really think that's one of the reasons they want you to do everything to 3 decimal places, because that forces you to be more accurate. So, again, I did not use that number, I used this number, and I got what I think is a better answer. Okay, but you did it right, you did it all right. And you put a nice little unit on there, feet per second, beautiful. How many feet did the penny fall during each 2-second interval? Did you get that far? So in the first 2-second interval, it was 64. Oh yeah, I think I'm right. And then 192, 320, and 448. So in the first 2 seconds, it traveled that far. Then it traveled this far, and so on. What do you notice about those? They're changing by a constant rate, right? Which is going to tell us something about our curve. All right, did you get to table 5? What did you end up with? So we had 0 to 2, and 2 to 4, 2 to 6, 6 to 8. All right, tell me what you came up with here for your average rates of change. Negative 32 feet per second. What was it, negative 96? Yep. How do we find average rate of change?
Oh,
We take, yeah, it's the difference divided by however the interval, like, so it's 2. So to get this one, we took 64 and divided it by 2. And those are negative because, yeah. Is the penny speeding up, slowing down, or falling at a constant speed? How do you know? Speeding up. And why is it speeding up? Yeah, it's pulling it down faster. So if it covered 32 feet in the first 2 seconds, but it went 96 feet in the next 2 seconds, obviously it covered around, so it's speeding up. Now we have to be careful because the next question, or one of the next questions, asks about concavity. This thing is speeding up, but the rates of change are actually becoming more negative, which means they are getting smaller, which means the curve is concave down. And is that what happened when you graphed it? Did you get something that looks like this when you graphed it? Hopefully. Yeah. All right, one more little exercise and then we're gonna do a little review. Back that page, the back of the penny page. We got another check your understanding. So you need to get all this up on the board. So I'll start setting it up while you start working on it. Excuse me. And when you come up, you don't have to show your work. You don't have room for all that. Yours, put your answers right here.
You have to do the second. Okay, how are we doing? We done already? Almost. Avery, can you give us the average rates of change you calculated here for these? Can you do that? All right, pop those up there for us. And we'll talk about B after we put that up there.
and see. How about this tape number 2? Anybody figuring out the numbers that go in this chart? Patrick, want to put them up there? All right, so what do we think about these? We're gonna answer these questions based on these. So what do we think about those? Charlie?
Should the signs be flipped?
Well, they should be. So let's make sure everybody's clear on that. When you do, let's say this is your interval, right, and we start that one. Your calculation should be f of 0 minus f of -1 over 0 minus -1, right? That's your calculation. So what's f of 0? F of 0 is 7, and f of -1 is 14. So does that make sense, Avery, and everybody else that maybe got it backwards? All right, so let's just. Now is it okay with everybody? So, find the rate of change of the average rates of change. So now we're taking these numbers and finding the rate of change. Well, what's happening here? They're going up by 2. This is what I was talking about at the very end of the period yesterday. See how all these intervals are exactly the same size? If I did a difference here, this would be the second difference now. If I did the difference here, I would get 2, and 2, and 2, and 2. And when the second differences are the same, this was the first difference right here. When I do the second differences, they are constant. That means I'm quadratic, which makes sense because it's parallel. Is it concave up or down? Obviously it's concave up, but how could you explain that? What's happening to the average rates of change? They are increasing, and increasing with concave up. And then what about Patrick's answers? I'll circle his. These are the ones he put in. Patrick, explain your logic to us, because these are like just a bunch of random numbers. So what was your logic?
If you take the rate of change for the y values,
Okay.
they're all decreasing by 3.
So this one we could calculate, because they gave us these numbers, and that rate of change is 7, or that difference is 7, and this difference is 4, which means that it's decreasing by 3, and if it's going to be quadratic, then that means they all have to decrease by 3. So this one would have to be 1, and this one -2, and then back this way, this one would be 10, and this one 13. Does that make sense to everybody? That is absolutely beautiful. All right, next page. I'm gonna start out. We're about out of time, so let me give you another piece of paper, and then next time we gather, we will start doing some review. There's some review there in your notes, and then here's another little review. That I put together. on these two reviews next time, we get together, which will be Monday.